Then let me start. Thank you for having me. It's nice to present our work on bootstrapping and building a verifiable notion on identity. So I will just jump right into the topic, and first we take a look at how identity management works in the current web. So you all know single sign-on, which basically requires you to register at an identity provider once, for example, Google, and then you can actually use your identity provider to log in at all other services with this one account. And so the nice thing about this approach is that you share your credentials only with your identity provider, so in this case Google, and it's convenient for users because users just have to maintain their one account and can log in everywhere. But and let's take a look at the details of how this actually works. So for example, you want to log in at eBay, and you want to use Google as your identity provider. Then eBay redirects you to Google, which then basically shares a login prompt to you that actually tells you that Google will now share your name, your email address, and your profile picture and so on with eBay. And then there's only the way for you to either accept or abort at this point, and then enter your credentials such that Google can verify your credentials and then provide you with some access tokens or identity tokens, depending on what kind of protocol implementation is used. Then you can reload actually the eBay page and basically pass the tokens to eBay, and then eBay can use these tokens either in their backend to authenticate you, or they can use the access token they got and further request some information about the users from specific resource services. And then once they have the data, they can share this with you, and this will be then displayed in the browser in your session, and the session starts. So what are problems with this approach, and can we do better? So that's the question now. And so, for example, the problems are that you have fixed data policies that you cannot really control. You have a lack of verifiability because typically the terms and conditions of identity providers are somewhat difficult to understand, and you don't really get who gets access to your data, who is able to compute on your data, and so on. And since Google and identity providers typically, maybe not Google, let's just talk about identity providers in general, they are typically centralized and are more easy to breach. And yeah, they can also, based on all the interactions they receive, they can start tracking you. So these are all things that raise some concerns. And what do we want instead? So we want to control our identifiers and control our data policies. We want transparent access logs that we can basically verify who gets access to our data. We want, if there happens computation on our data, we want actually verify if this data, if the algorithms and the consumers who compute on our data comply with certain policies that we set up in our data policies. We don't want data breaches, obviously, and we also want to provision verifiable data. So these are the points that the technologies that I'll present now address. And yeah, basically the question is, can we go from this centralized sort of infrastructure where you have the identity service that is centralized and the resource service that is centralized, go to the decentralized setup where we basically have the blockchain as the identity service, and we have decentralized storage networks for the resource service. And so now we take a look at technologies that allow you to actually build this verifiable notion of identity. And here and there I will point to some interesting research papers that actually mainly are responsible for developing these concepts that I will present. So let's start with the basic building blocks to build a decentralized identity. So first you have wallets on the user side. Wallets actually give the users access to cryptographic material that is used to interact with the blockchain ecosystem, because you have to perform transactions, you have to manage some addresses and so on. So this is all handled by wallets or connected to wallets. And so there is the question of having custodial wallets, which means that users manage their wallets themselves, or you have non-custodial wallets where you have a again, a third party that helps you with the management, or you can even have a shared custody based on multi-party computation concepts, where actually a third party together with you handle the management of the wallets. And an interesting paper is that I like to point to is the paper on MFKDF, which is a multi-factor key derivation function. And so this allows you to actually not only use a password to derive your key, but to use multiple authentication factors such as email, like your authenticator one-time passwords and other types of factors to derive your key, and this way achieve actually the properties that non-custodial wallets provide, but you actually achieve that while still having this custodial wallet. Then the next thing we need smart contracts for address management. And typically what you have is if you basically go to eBay, for example, and you provide eBay with the address that is derived from your wallet, then eBay should look up the address and can do this in the smart contract. And then the smart contract, basically, they're typically registry contracts that have the same address. So eBay can always go to the registry contract and from there decide on what kind of resolver they want to access to get to data that you link via your on-chain account. And third, you have decentralized storage networks where you intend to store encrypted data. We can in the first place now assume that you store data in plain, and with these components basically the process is as follows. So similar to the single sign-on example I showed in the beginning, users can store their data on decentralized storage networks, and then they can use their blockchain address from the wallet, present this to eBay. eBay can then go to the smart contract to resolve actually the location identifier of your data, and then get to the resource service and pull your data. But what's next? Like this would be the very basic identity management in a decentralized context. What we want to have is we want to protect our data actually. And so when it comes to data protection, we actually need to outsource the secret management, the secrets that protect our data to a different service, because otherwise there is no availability of the secret information. So the idea is actually to put the secrets on-chain or basically to some other entities. We cannot today put our secrets on the chain directly because blockchains lack a secret management functionalities, but there is also research on how this can be achieved. Actually, this paper right here proves a line of research, and so there are concepts of showing how this is possible. But for practical reasons, the idea is that you also use a decentralized off-chain network and split up your secret into multiple shares and share it with the secret management committee, such that the resource consumer can basically request the shared secret from this committee. And so how would the process of decentralized access control look like? It's described in the Calypso paper. So what you do is, as the resource owner, you encrypt your data, put it into the IPFS, and with the symmetric key that is used for encryption, you split this up and share it with the secret management committee, and you register a data policy on-chain. And so for the consumer now to access your data, what the consumer has to do is the consumer now needs to post a transaction to the identity service, so to the blockchain, that complies with the data policy that you set up. And then in a second step, the eBay can actually now go to the secret management committee and request your decryption secret and the shares. And the secret management committee basically monitors the smart contract, and only if there is a valid transaction, sort of data retransaction posted to the blockchain, then the secret management committee will hand out their shares, such that eBay can reconstruct actually the decryption secret and then pull your data from the decentralized storage network and access your data. The thing is that enough, or can we go even further? And the answer is yes, we can, by using secure computation. And the idea is actually that you never give access to your data, but instead give access to the computation result on your data. And if the computation happens in a secure way, this means that the output of the computation does not reveal anything of the inputs that basically went into the computation. And so there are multiple technologies to implement secure computation. There is fully homomorphic encryption, for example. There is trusted enclaves, and there is multi-party computation. So these concepts, these are the three main concepts that achieve secure computation. They have some trade-offs. For example, trusted enclaves are very efficient and scalable and fast. However, they are centralized. That's something we don't really want in this environment. Then there is multi-party computation, which introduces some communication overhead, but achieves a degree of decentralization. And then there is fully homomorphic encryption, which exists, but is not really scalable. And so it's also not yet supported on blockchains itself. And so this is why there are different approaches actually to perform secure computation and do this. And so you can think of doing secure computation on the blockchain itself. So that would be the nicest thing if the blockchain would support secure computation. However, blockchains are typically not supported with trusted enclaves. There are blockchain projects that do that, but generally, like we stick with Ethereum for now, it's not supported. So you again have these off-chain compute committees that leverage these different technologies in order to provide secure computation. And so now then the idea is to implement basically what I said, to give access to the output of secure computation results, however, in a way that it's fully coordinated by blockchain stems and digests that allow you to actually verify that the program that is running on the compute node actually has been audited, and there is a proof of program compliance that basically matches the data policy you put out. And then you also want, from the secure computation nodes, you want some form of digest that the computation has been performed correctly. TEs can do remote attestation. Multi-party computation, you typically combine this with zero-knowledge proofs to show computational integrity. And fully homomorphic encryption is something that you could directly run on-chain, but this is not practical yet. So these are things that actually you want to have registered on the chain before you hand out actually data to the consumer. And now, so far so good. So we basically now with the ecosystems or concepts I showed you, you can achieve control of identifiers, you can achieve control of data policies, you have transparent access logs, because the thing is you can basically require all the consumers to post something on-chain that complies with your policy. So this way you get transparency and see who is basically doing what on your data. And then you get verifiable policy-compliant computation. And hopefully in a decentralized setup, it's more difficult to basically breach data. However, the question remains, how do we provision verifiable data? And this is a big question, because eBay could ask, is the data you actually put here in the decentralized storage, is it authentic and is it trustworthy? Or did you just put random data, came up with random data and put this into the storage? And especially if you're basically a seller on eBay, they have some know your customer requirements that might require you to provide your address and your age, for example, like multiple things to eBay, and share this with eBay, and eBay basically must know whether this data is trustworthy or not. And I'd like to mention here, so there is this ecosystem of verifiable credentials where you typically have trustworthy issuers that are registered on-chain and so on. Like you have all these nice assumptions that reputable issuers exist that can be represented on-chain. However, that's not really the case. That's why also basically decentralized identity systems, like in the style it is communicated, do not really exist as of today. And so can we actually build issuers? And the answer is we can, by using data provenance oracles. And so the idea is here, now the resource owner wants to, now in this case, prove the address and age. And basically get the address and age verified by an issuer. In order to do that, the resource owner connects to the Mitarbeiterservice Bayern, for example, which is a trustworthy source that at some point verified your data, hopefully. So that's the assumption here. And then you take like one external service, which is the Oracle verifier, and now you perform basically an API request against the API of Mitarbeiterservice Bayern. And the Oracle verifier and the resource owner, they both represent the client in this interaction. And what you do is you first have so in TLS, you typically have a handshake phase and then a record layer phase. In the handshake phase, the secrets are negotiated. In the record layer, the traffic is then authenticated and encrypted. And what you do is, instead of a like Diffie-Hellman two-party handshake, you perform a three-party handshake, such that the handshake secrets that the verifier has and that the resource owner has actually are additive shares. And if you add them together, they basically make up this handshake secret that exists at the server. And so the server here continues to use the handshake secret to derive like the session keys and then also use these session keys to encrypt the data. On the client side, you must do the same thing. However, the idea is that the resource owner never discloses the secret share, KP, to the verifier, because otherwise the verifier would get access to the data that is communicated. And on the other hand, the verifier wants that the resource owner is not able to cheat and inject any false data into the protocol. So that's why the verifier keeps the secret to himself. And now in secure computation, as introduced before, they can, in a two-party fashion, compute the key derivation of the session keys and then compute the authentication tags for the messages. They can only do this together. And this way, basically, the verifier basically knows that the resource owner cannot cheat, and the resource owner knows that the verifier actually never can access the data that is requested. And then you can even extend this protocol and commit, like the resource owner can commit the response such that the verifier can disclose the key share. The resource owner anyways is the owner of the data, so he can access the data and then compute a zero-knowledge proof, which basically shows, so the circuit of the zero-knowledge proof shows that the commitment of the response is successful, that the decryption of the response maps to the underlying data, the address and age, and then if you verify this on the verifier side, the verifier adds the signature on your data, and now you can use the signature, store it, and present it to eBay, who then knows that the data is trustworthy. And so if you're interested in basically all I presented, we have an upcoming SOK on data sovereignty, which will be out in a month, I think, at EuroSMP. We also have a GitHub repository which goes into all these technologies, and we have upcoming work on TLS-oracles. And thank you for listening.
Thanks a lot.